Okay, students, at the end of the last video, we had just finished this problem looking at the probability that a value is between two specific numbers when that value is normally distributed. And this is actually an add-on to the same problem. So we're on slide 11. It says if 200 shoppers enter the store, how many shoppers would you expect to be in the store between 24 and 54 minutes? This is a lot simpler than maybe it looks at first blush, because we already know the probability that someone's in the store between 24 and 54 minutes. That was 0.7333. So 200 shoppers enter the store, about 73% of them, or about 147 shoppers, are going to be in that store between 24 and 54 minutes. Let's try a different probability problem. This time we're finding the probability that the shopper will be in the store for more than 39 minutes, and we're reminded that mu equals 45 and sigma equals 12. This is on slide 12. All right, well, we're going to have to do the same kind of transformation that we did before. So we have probability x is greater than 39. And we want to transform that so that we have a standard normal probability to work with instead. So we know we're going to have to transform that first x into a z. And because we're transforming that x, we also have to transform the 39. So we are going to start by subtracting 45 from both sides. And then we're going to have to divide by that 12 on both sides. Remember, whatever we do to one side, we have to do to the other side. All right, well, that x minus 45 divided by 12 is our z. So what we're saying is that the probability that x is greater than 39 is the same as the probability that a z random variable is greater than negative 6 over 12, which is the probability that that z is greater than negative 0.5. And that is something that we can figure out using a standard normal table and the complement rule. So making that transformation so that we can find that probability z is greater than negative 0.50, we're going to have to find the probability first that a z is less than negative 0.50, because that's what our standard normal table knows how to do. It knows how to find cumulative probabilities from negative infinity up. Once we've done that, then we're going to take 1 minus that value, and we're going to find that the probability that a shopper is in the store for longer than 39 minutes is about 0.6915. All right, last piece of the problem. This is on slide 14. If 200 shoppers enter the store, how many shoppers would you expect to be in the store more than 39 minutes? We know that the probability the shoppers in the store more than 39 minutes is about 69%. So 200 times that 0.6915 equals about 138 shoppers that will be in that store longer than 39 minutes. All right, well, that was a pretty big, long problem, but we made it through. We're now going to move on to a different concept. So we just finished up chapter 5.2 in our book, so we're moving into 5.3. And in section 5.2, we were given a normally distributed random variable x, and we were asked to find a probability. Now we're going to be going the opposite direction. We're going to be given a probability, and we're going to be asked to find the value of the random variable x that goes with that probability. So we're going to go backwards, and yes, we're going to use our standard normal table, but this time, instead of looking at the first column and the first row to figure out a z value or a z-score, we're going to be looking for a probability in the middle of the table and then tracing our way back out to what that z-score is that goes with that probability. So let's get started. We're on example 7, which is on page 16. And we're being asked to find the z-score that corresponds to a cumulative area of 0.3632. So what are we going to do? We're going to go look at our table, and we're going to look for that 0.3632 or whatever's the closest. And because this is a store-bought problem, we're going to be able to find that 0.3632 right on that table. When we find it, we're going to have to trace out along the row to see the negative 0.3 in that first column. And then we're going to have to trace upwards to that first row and find the 0.05 to add to that. So basically, the z-score we're looking for is negative 0.35. Following the guidelines here, the values at the beginning of the corresponding row and at the top of the column give the z-score, and there we are. All right. Find the z-score that has 10.75% of the distribution's area to its right. So let's draw that so we can see what it would look like. So here's our standard normal distribution, and we're asked to find a z-score that has 0.1075 to its right. That means that the area under the curve from that z-score up is going to be 0.1075. Well, again, our table only knows how to look at cumulative areas from negative infinity up, so we're going to have to figure out what the probability is that goes up to that z. How do we figure that out? Well, we're going to take 1 minus 0.1075. Moving along, there it is. Because the area to the right is 0.1075, the cumulative area is 0.8925. And we're going to have to go look that up in our table. So let's look for it. Do we see it? I see it. It's right there. So again, we're going to have to go out and up to see that the z-score that corresponds to that is 1.24. And following our slide set, we can see that indeed the z-score is 1.24. All right, now you may not remember this, but when we went over percentiles, we talked about that being the 5th percentile. So let's look at the standard normal distribution and see what that really means. Well, if you're in the 5th percentile, that means you've got 95% of the probability above you and 5% of the probability below you. So what we're really looking for is the z-score such that 0.05 is the cumulative area below that z-score. And there we go. All right, so we're going to have to look at our standard normal table, and what we're going to discover is that in the table what we have is 0.0495 and 0.0505, so somewhere between a z of negative 1.65 and a z of negative 1.64 is the value we're looking for. And actually, I happen to know that the z-score is exactly between those two numbers, and the z-score of interest is negative 1.645. Okay, let's say we, instead of wanting to find a z-score from a probability, we actually want to find an x-score from a probability, meaning we know that x is distributed normally with some mean, some standard deviation, and we know that we want to find the probability related to x. Well, it's not going to be so bad. We're basically going to transform backwards. So remember we were saying z equals x minus mu over sigma. Using a little bit of algebra, we can multiply both sides times sigma. That gives us x minus mu equals z sigma. Then if we add mu to both sides, we get back this equation here, x equals mu plus z sigma. So we're basically going to have to transform our z-score. First we'll look up our z-score using the probability we're given, and then we're going to have to transform it into our x-score using this equation. So here's an example. A veterinarian records the weights of cats treated at a clinic. The weights are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. So now we know x is distributed normally with mean 9 and standard deviation 2. Find the weights x corresponding to the z-scores of 1.96, negative 0.44, and 0. So actually finding the solutions for this problem is not that difficult. We're just going to plug in our numbers into our equation. So we have our mu equals 9. That's going to go where mu is. 2 goes where the sigma is. And then whatever our score that we're calculating for is, we're going to plug that into z. So literally, we're just plugging and chugging. This is called a plug and chug problem. So for example, for z equals 1.96, the equivalent x value is 12.92 pounds. 9 plus 1.96 times 2 gives you 12.92. For z equals negative 0.44, the answer for x is 8.12 pounds. Again, we're just plugging in those values. And finally, for z equals 0, we have x equals 9 pounds. One thing to notice is that z equals 1.96 is above the mean being 0, and so is 12.92 pounds. Z equals negative 0.44 is below the mean, and so is 8.12 pounds. And then for z equals 0, remember 0 is our mean, we get back just our mean for the x. Okay, one more problem in this set of slides. Example 11 on slide 23. Scores for the California Peace Officer Standards and Training Test are normally distributed with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? So what do we know? We know the distribution of scores, called x, some random variable representing a score. The distribution of scores is normal with mean 50 and standard deviation 10, right? And we know that we're interested in the top 10% of the distribution. So we're going to be using the standard normal in order to find that score that goes with the top 10%. Top 10% means that we want 0.10 above that z-score and 0.90 below that z-score. So we're looking for the z-score such that the cumulative probability below it is 0.90. Once we have that, then we know what we need to do. We're going to transform using x equals mu plus z sigma. We know our sigma is 10. We know our mu is 50. So we just need to have that z-score that we get from that distribution to plug in, and we'll be all set. So here's our solution. We need to find that z-score such that 10% of the probability is above it, or 90% of the probability is below it, and then transform it to get our x back. All right, well, it turns out that the z-score, if you go and look it up in the table, is going to be 1.28. 90% of the area under the curve is below z equals 1.28. We can then transform that, plugging in the 1.28 in for z. We already knew we had to plug in 10 for sigma and 50 for mu. And if we plug all that in, we get an answer of 62.8. So the lowest score you can earn and still be eligible to be hired by the agency is about 63. All right, guys, you just learned a bunch of new techniques. Go try them out in the homework, and I'll see you in the next slide set. Bye-bye.